Thanks very much. So the evidence is clear. Our climate is changing rapidly, and particularly in the polar regions. As Rachel just pointed out, I've been both to the Antarctic and the Arctic, and so you'll see I'm bipolar, I guess, as it were. And so you'll see a lot of photos, such as this one, on our most recent Antarctic expedition. And I'd like to tell you about some work that we've been doing that I've been involved in actually since, or got interested in this since high school when I started working at NASA, looking at satellite images of sea ice in the Antarctic. And I'll tell you about how we're using mathematics to try to understand what's happening with sea ice in the polar regions and how to maybe better predict what might happen in the future. So why study sea ice? Well, it covers, there's a lot of it. There's less now than there was, but it covers about, so everybody says, Ken, you got to work fast because it might all go away. It covers about 7 to 10% of the Earth's ocean surface in the polar regions. It's the boundary layer between the ocean and the atmosphere, and these two principal geophysical fluids, namely the ocean and the atmosphere. And as such, it mediates the exchange of heat, moisture, and momentum between the ocean and the atmosphere. This is actually the ship's track, a lead formed by the ship's track of the Aurora Australis, which is the main Australian icebreaker I've now been on 3 times, and you see heat rising up in the form of sea smoke through this lead. And sea ice is particularly important in that it's this thin layer of ice on the ocean, and it's not only a leading indicator of climate change, but it plays a fundamental role in the Earth's climate system. Here's a schematic diagram showing the atmosphere and the ocean, say off the coast of Antarctica. And it plays a large role in interacting with the ocean below as well as the atmosphere above. And here you see the ice, say, forming here. And as sea ice forms, it's salty water, of course. It's not pure water. And as salty water freezes, it tries to reject the brine, the salts, because the salts cannot be incorporated into the crystalline structure of the ice. And so below an advancing ice water interface, there's a highly concentrated layer of brine, and there's actually a dendritic platelet structure at that interface, and the brine, this highly concentrated salty water, gets trapped in between these platelets of ice. And so sea ice is actually a composite material of pure ice with brine inclusions. And actually, that's my background as a mathematician, is studying composite materials, and sea ice is a very interesting example of this. And another way, however, this rejected brine then particularly in the Antarctic, forms what's called Antarctic bottom water. You get these cold, dense plumes of salty water that collect and then form in the Antarctic, which is called Antarctic bottom water. And here, actually, this is a photo of the Aurora Australis that I took on our most recent expedition, another image of the sea ice. And these cold, dense plumes forming this bottom water is what drives deep circulation throughout the world's ocean system. And this is known as the global thermohaline conveyor belt, here being formed in the polar regions and then running like a complex river system throughout the rest of the world's ocean system. And of course, this is, say, the Gulf Stream here, which keeps Europe warm, but these particular patterns in the ocean are dependent on very subtle balances of salty versus fresh water and so on. So one of the things that people are concerned about, of course, is Greenland, as the Greenland ice sheet, say 2 miles thick of pure water, pure ice, fresh water, as that starts to melt and provides a significant input of fresh water, it could perhaps disrupt the delicate balance that this complex conveyor belt system depends upon. So one of the key roles that sea ice plays in the global climate system is in reflecting incoming solar radiation. It's, roughly speaking, Earth's refrigerator. So one of the key aspects of sea ice is its solar absorptivity. Not that we're going to make solar cells out of it or the ocean surrounding. However, one of the things that drives what's happening in the polar regions is the mismatch between the solar absorptivity for white snow and ice versus darker seawater or ocean, and land as well. And so here's an image showing the typically white North Polar region, and all that incoming solar radiation is being, or most of it's being reflected back into space in the summertime when the sun is up there. However, in a melting environment where a lot of that sea ice and white surface is gone, instead of the Arctic Ocean being protected from further absorption and further warming, it's now absorbing that incoming solar radiation. And this mismatch between the white surfaces and dark surfaces, accentuated in the polar regions, leads to what's called the ice albedo feedback. And so here's actually a picture of in the Arctic where these melt ponds that appear in May and June are particularly significant. And so these are darker patches on the surface of the ice, which then, of course, absorb much more. And, of course, when you have more open water, you're getting much more absorption as well. And so with increased melting and warming, you lower the albedo of the overall ice pack, which then leads to increased absorption of sunlight, which then further leads to more melting, and so on, and which then leads to lowering the albedo and more absorption of sunlight and more melting, and so on, in a positive feedback loop. So this is one of the nonlinear feedbacks that's particularly significant in the polar regions. That's where some of the interesting mathematics starts to come into play. And of course, one of it's like a runaway train, though. You get this effect going, and then it feeds on itself. So as you could see from that previous picture, the sea ice albedo, the overall reflectance of the ice pack, is controlled largely by these melt ponds. And whether or not these ponds pool up and get larger, or whether or not they drain, is controlled by by how easy it is for fluid to flow through the sea ice. And this leads us to one of the fundamental parameters that we're interested in this talk, that I will be interested in a bit, is the fluid permeability of the ice as a porous composite material. Actually, this is a photo of me taken by Don Perovich, who's a well-known Arctic scientist who's studied this ice albedo feedback a lot and is really Mr. Melt Pond himself. And year after year, most of the Arctic scientists will wear these knee boots or whatever up there, but I would always wear these basically a green rubber suit, which are essentially green waders, and somehow I became known as Frogman as a result of this, wearing this year after year. But anyway, I guess this was about a year and a half ago up in the Arctic, and you can't see it here, but the melt ponds were so deep that Frogman actually had to do the melt pond measurements, because all the other guys would have had their boots inundated. So I'm moving along a transect line here. This is a photo that Don took of me actually making the measurements of these melt ponds as you move along a particular transect. Now, what's one of the things that's significant and has been, of course, in the news is the loss of the Arctic ice pack. Now, in the wintertime, we're not seeing such dramatic declines. I mean, this is over a 30-year period, and since 1978, and you see a gradual fall off of the areal extent of the winter Arctic ice pack. And this dotted line here represents, say, about a 20-year average from about 1980 to about 2000. And so you see a gradual decrease in the extent. However, what is very significant and is somewhat alarming is the dramatic decline of this summer Arctic ice pack, which is, of course, the key for protecting the Arctic Ocean from further absorption of solar radiation. And so basically, we have a sort of a fall off and then a slight increase, and then things really fell off the map in 2007. There was a record decrease and a record minimum, and things slightly bounced back in 2008, and we're right about at that level now. And one needs to ask the question, with such a dramatic change, have we passed through a so-called tipping point or a critical threshold? Yeah? This is percent difference from that average, from that 20-year average, basically. Okay, And so in 2007, there was an increase in open water fraction that resulted in a 500% positive anomaly in solar heat input into the upper ocean. That would make a great stuff. You could do that kind of efficiency for solar cells, triggering this so-called ice albedo feedback. But now, whereas there used to be really, really thick ice, this thick multi-year sea ice, much of that thick multi-year ice is gone now. And so we're in a different regime for sure, whether or not we've passed through a so-called tipping point. I'll mention a technical tipping point in the sense of dynamical systems. I will mention a few words about that in a second. To put this in some geographical perspective, the summer Arctic ice pack in 1980 was covered most of the Arctic Ocean. The areal extent happened to correspond to the continental United States without Arizona. Nothing against Arizona. That's just the way it worked out. So by 2005, we lost the area in red, which corresponds to the United States east of the Mississippi. But then amazingly, within the next 2 years, and this is this runaway train effect of the ice albedo feedback, is we've lost this huge swath of the Midwest denoted in purple. And as I was just briefly mentioning, from there's been an interesting dynamical systems analysis of this so-called tipping point issue, where one looks at the differential equations associated with this ice albedo feedback, and you can ask the question, has a critical threshold been crossed in a transition, say, from an ice-covered to an ice-free Arctic Ocean? And they found that at least in the transition from a current perennial sea ice conditions to at least to seasonally ice-free conditions, like an ice-free summer, that this is somewhat unlikely. However, if there's further warming to a completely and a sudden loss of wintertime ice as well, that there would be such a critical point or a critical transition from which we wouldn't recover. Now, to put this in a global perspective, the Antarctic is already in such a seasonal regime, pretty much. In the wintertime, you get this big ring of sea ice surrounding the Antarctic continent, and then by summertime, most of it melts. This is actually the Weddell Sea. This is probably the largest extent of at least persistent summer ice. And actually, that was my first expedition in 1980 when I was an undergraduate at Dartmouth. And I think we were the second expedition to go into the western Weddell Sea since Shackleton, if you've heard of Shackleton's exploits. And but the point is that most of the ice disappears in the summertime in the Antarctic, whereas in the Arctic, in the wintertime, of course, you get this massive extent, but then it, of course, decreases, but now it's decreasing a lot more. And so one must ask the question, is global warming Antarctifying the Arctic? Is the Arctic becoming this seasonal ice cover, basically? But no matter what, climate change is being amplified in the polar regions. And here this is showing at least the state of affairs about a year and a half ago, showing so most of this used to be completely covered. And so now, for example, the polar bears have to trudge all the way out here to get to the ice and so on. It's quite a significant fall off, obviously, of this ice pack. Now, one of the things as a scientist and a mathematician, one who wants to predict what's actually happening, as most of the scientific community does, what's particularly alarming is the IPCC Intergovernmental Panel on Climate Change Projections, where they run, say, the 20, well, all sort of lots and lots of scientists worldwide will run about on the order of 20 of the world's best climate models, and to try to predict what's happening to global climate, what kind of increases in global temperatures you'll see, but in particular, in this case, what is the fate of the summer Arctic ice pack? And they all predict that it'll basically disappear. The question is how fast, or how rapidly are we approaching that kind of regime? And they all, sort of at least the full range of all these 20 best models are predicting that at least by the end of by late 21st century, by the end of the 21st century, we should be pretty much in a summertime ice-free regime. This is a later analysis of all these runs. But what's alarming is that the actual data is over here. We're experiencing a much more rapid decline than any of the world's best climate models have been able to capture. So clearly we're not understanding something. Clearly there are things that are going on that we're not capturing in these models. And our work is somewhat devoted, at least to some of the smaller scale processes that are important on a big scale for such predictions. Now, in the Antarctic, global climate models, certainly with warming, certainly predict that there will be declines in the average annual ice area and volume. However, this is over the last, say, I guess about almost over 30 years, showing increases versus decreases in ice concentration. You see the yellow is slight increases, actually. But of course, now we're in this seasonal regime already, so this is really mostly wintertime ice. There, of course, are some significant regional decreases off the western Antarctic peninsula, where people are concerned about also the collapse of the western Antarctic ice sheet. And this is the question of sea level rise, and when all this fresh water from that's stored in the world's glaciers and ice caps on Antarctica and Greenland, which is different from sea ice, of course, if that gets dumped into the ocean, and question of how much is sea level going to rise. And there have been significant losses in this particular region, although there have also been significant increases off the Ross Sea as well. So clearly there's definitely a lot of things that we don't understand about what's going on in Earth's ice packs. So let's explore some of the structures that one encounters in looking at sea ice, and some of the key processes which we must understand better and represented more realistically in climate models. And of course, as a mathematician, I'll try to show you how mathematics can help improve the predictions as to what might happen to Earth's ice packs. So first, just a couple words about, and I've really suppressed the equations here, but because it gets to be kind of involved. And so what is essential in a numerical sea ice model for climate studies? Well, you'd like to be able to simulate the climatological mean annual cycle of the ice and snow. You need to represent sensitivity to perturbations, must have the key feedback effects, such as an accurate representation of the ice albedo feedback. And particularly, this is one of the things that I'll really focus in on, is you need to have physics that's appropriate to the model's spatial scale. In other words, you need to be able to incorporate key processes that are, in some sense, subscale, and how do you parameterize them into these larger scale models where the typical grid size is like 30 kilometers or 50 kilometers or 100 kilometers, depending on the kind of model that you're running. But I'll be talking about processes that are on the sub-millimeter scale, but they turn out to be very important for these much larger scale issues. And so there's a translation. One of the key issues here is the translation across scales. What are the key ingredients or governing equations that need to be solved on very big, powerful computers? Well, the ice thickness distribution evolution equation, which involves both the dynamics and the thermodynamics of the ice, is key. This is, in some sense, the holy grail. If you don't have the right initial conditions to run your simulations, well, after a certain number of years, you're going to probably be pretty far off. However, from an electromagnetic perspective and a remote sensing perspective, this is clearly one of the most difficult things to get your hand on, because sea ice is salty, and so it absorbs electromagnetic waves. And so this is a very challenging problem as to how you get really good information about the thickness of the ice. It's highly non-trivial. And actually, some of the things that I'll talk about later on will be directed at some of these methods. Conservation of momentum, essentially F equals ma for sea ice, and coupling the atmosphere and the ocean through the sea ice and how heat is exchanged is another one of these key equations. And the sea ice dynamics, constitutive law, stress versus strains relations, treating on a very large scale, on a global scale, treating sea ice as a plastic continuum. These are some of the key equations and relations that need to be incorporated into these models. Here's just a kind of a cool picture showing the ice thickness distribution function. G is a function of in two-dimensional space, looking down from on the surface of the ocean, and as a probability density as a function of height and time, where H is the ice thickness. Mechanical redistribution as ice flows crash together and basically form ridges and so on. You transfer probability density from the low end up to the higher end, or as you grow ice on open water, you transfer probability, or you can accomplish, I guess, advection in the thickness space from down at the low end up to the thicker ice. G is this distribution function for right. It's a probability density function, basically. Okay, so now some key features of sea ice and its marine environment, which are relevant to modeling climate. As I said, sea ice is a composite material. I find it to be an extremely interesting. Actually, this is what got me involved in composite materials as a mathematician. My early studies in high school and college on sea ice. Pure ice with brine, air, and salt inclusions. I'll focus primarily on the two-phase nature, the ice and the brine. These are sub-millimeter scale brine inclusions that are laced throughout the ice. It exhibits multi-scale structure over 10 orders of magnitude. Here's the sub-millimeter scale brine inclusions. It's polycrystalline structure, similar to metals and other crystalline materials, which we look at under cross polarizers to get a sense as to how the ice was grown and so on, and what its substructure is. These brine inclusions coalesce together and form large-scale brine channels. This is a horizontal cross-section photo I took in the Arctic. Actually, these are almost like diffusion-limited aggregation structures. I'll show something about that in a second. These huge pieces of ice are really cool. They have a really Dave Cole at Crell, which is where I did my work as an undergraduate. While I was at Dartmouth studying sea ice, they take this massive chainsaw with a bar that's about 8 feet long, and it runs on train tracks. And they do a slice through the ice, and then another slice nearby, and they pull it up with a crane, and then you get these beautiful images showing these big brine channels. Here's a meter scale showing pancake ice in the Southern Ocean. You'll see that in the video when I show you. It's very, very beautiful behavior. Coalescing pancakes to start to form the ice pack. Meter scale flows up here, and then now in the middle we're looking from the helicopter scale. So that's that orange over there on the left is the Aurora Australis, which is about 100 meters long, about the length of a football field. And then from space, you see here. This is off the coast of Japan, Sakhalin Island in the Sea of Okhotsk, and looking at the sea ice there, showing, again, from my perspective, a beautiful two-phase composite, a time-evolving two-phase composite material. Okay, the sea ice pack also exhibits fractal structure, displaying self-similar behavior on many length scales. And this is not just of academic interest, but this flow size distribution and the relationship between the perimeter for lateral melting versus the area for bottom melting and albedo effects and so on. This is actually a very important aspect of the ice pack, which has certainly not been incorporated into these models. Roughly speaking, bigger flows are easier to break while smaller flows are easier to melt. This is so-called Apollonian gasket, which was, I think by the Greeks, which is one of the first sort of fractal type structures. This is the Sierpinski gasket, and this is a naturally occurring fractal, also known as cauliflower. And so this is some images showing the self-similarity of sea ice flows. This is actually the Polar Stern up there, the main German research icebreaker. And so you blow this little area up here, and it looks very similar. It turns out there looks like there are two regimes for fractal dimensions. Flow sizes in 1 to 20 meters. There's one kind of, seems to be a universal fractal dimension, and then different fractal dimensions at larger length scales. And we actually have some work going on now looking at fracture of ice and trying to understand some of these fractal structures in sea ice. On a much smaller scale, the brine channels exhibit fractal structure. This is cross-sections of brine channels, and actually this is so-called diffusion-limited aggregation clusters, which come up in a lot of really interesting applied areas, and we're looking at some of the relationships there as well. Also in some suspensions called electrorheological fluids, which are suspensions of particles in a viscous fluid where you apply an electric field, and when they're metal, you get structures that look just like this. It's pretty spectacular, actually. Sorry? Like liquid snowflakes. There you go. Okay. Another very interesting one, some of these subscale processes that are important to understand in the context of larger scale climate models is so-called polynyas. These are like ice factories. This is the Mertz Glacier polynya right off the coast of East Antarctica. I've spent a couple of months of my life in there. I've spent a fair bit of time in my life in Antarctic polynyas. And the polynya is a Russian word meaning ice-free region. And basically the deal at the Mertz Glacier is that you get these cold, dense, katabatic winds screaming off the continent. It gets really cold around there. It blows the ice out, but it's wintertime, so now you got open water, so you freeze more ice. More katabatic winds blow the ice out. then you get open water freeze the ice. So they're like ice factories. And so while the Mertz Glacier polynya is only covers about, what, I guess 1/1000th of the areal extent of the overall Antarctic sea ice zone, it accounts for about 1% of the total production in the Southern Ocean. On the larger scale, there's a lot of coastal polynyas. Around 10% of the Southern Ocean sea ice is produced by major Antarctic coastal polynyas, but they're just these tiny dots along the coast. And these are not well accounted for or understood in the context of these global models. So these are important subgrid scale processes. And then another one, which has helped to been used to partially explain why we've lost so much ice in the Arctic, is first of all, and this is Wisla Maslowski at the Naval Postgraduate School, who's asked the question: was the Arctic ice pack preconditioned for dramatic declines that we've seen? There was anomalous export of sea ice through the Fram Strait during between Greenland and Iceland during the 1990s, and then through higher resolution Arctic Ocean models, he's been looking at the accumulation of heat in the Western Arctic, that place where most of that ice is now gone, via advection from the Pacific and Atlantic perhaps, which could perhaps have been a critical factor in thinning the ice pack, which then makes it much more susceptible to this so-called ice albedo feedback. So these are some of the processes that are probably playing a role in some of the things that we're seeing, that we're observing, but not that well understood or not been incorporated properly into these models. So now I'd like to focus on fluid and electrical transport in sea ice, the microphysics, which underlie some of these processes, especially this ice albedo feedback and some other key processes that I'll tell you about. Fluid transport in sea ice is important to both the geophysics and the biology of the polar regions. As I mentioned a few minutes ago, the electromagnetic transport in sea ice is very important to remote sensing of the polar regions, and in particular monitoring climate change and trying to get a handle on ice thickness. And our work on fluid and electromagnetic transport in sea ice can help these global climate, biogeochemical, and remote sensing models to hopefully refine predictions of climate change and how ecosystems may respond, but also to monitor the impact of climate change through looking at the state, trying to quantify the state of the ice. There have been a lot of people involved in this endeavor that I've been on now. My main collaborator is Hayo Eichen up at the University of Alaska Fairbanks, some of his students and postdocs. At the University of Utah, Jingyi Zhu has done a lot of the numerics. I've had a lot of students involved in this highly interdisciplinary endeavor. I've had students from, most of these started with calculus, my Calculus 1 class. Amy Heaton, as a chemistry major, walked up to me and said, Ken, I want to do sea ice research from my undergraduate work, and she did. She was, I think, she was the first person I took up to the Arctic with me, actually. So all these students, except for I think one of them, have been to the Arctic with me. And then most recently, Adam Gulley, who started with me as an undergraduate, he went to the Antarctic with me, and you'll see him in the video that I'll show you at the end. And these guys here have been very helpful in setting up our experiments and so on when we go to the locals, inhabitants down in Antarctica. So one of the key results here, which permeates so much of what happens on the small scale in sea ice, which then affects larger scale processes, is something I discovered by going to Antarctica about 12 years ago. I started getting interested in it about 15 years ago. And it's basically the on-off switch for fluid transport in sea ice. This is old data that is not permeability per se. It's a proxy for permeability. It's measuring the rate of change of salinity basically due to brine drainage. And as you increase the temperature, the brine volume fraction increases. This is 5%, 10%, 15%, and so on. And what you see here is that below a critical brine volume fraction of about 5%, the sea ice is effectively impermeable. Whereas when the brine volume fraction exceeds about 5%, at least for columnar sea ice, the classic Arctic congelation growth sea ice, the sea ice is increasingly permeable. And this, I observed that this critical brine volume fraction of 5% for a critical temperature of -5 Celsius, for a typical bulk salinity of 5 parts per thousand corresponds to a critical temperature of -5 C. So because of all the fives, I just called this the rule of fives. And now it's really permeated the sea ice literature, because as you'll see, it controls so many of the the processes that go on in sea ice. One of them, which is actually what got me started in all this and got me interested in this, was I was very lucky to have gone into the eastern Weddell Sea back in 1994. We were the first expedition in the wintertime to go into this huge polynya. That's not really there anymore, although it's some of the processes that kept it going are still happening. Instead of seeing a big hole in the sea ice in 1994, we measured incredible vertical oceanic heat fluxes coming up through the ocean, especially during storms when you get convection rolls going in the upper ocean. And however, we saw a seemingly stable 50-centimeter ice pack, even though it was being melted at the rate of about 5 centimeters a day during storms. It wasn't going away. It was stable. And what was happening was it was a surface flooding phenomena where you get snow loading from snow piling up on the surface, pushing it down, creating a pressure head, and then seawater percolating up to flood the surface. And you see this all over the Antarctic. This is a very important process that actually, you get this slushy mix on the surface, storm goes away, and that slushy mix forms so-called snow ice. And this actually accounts up to, overall, in the overall Antarctic ice pack, between 20 and 40% of the ice that's created. And these kinds of processes are not incorporated into these main climate models at this point. They're being incorporated, but they have not so far. And of course, this is all controlled by the permeability. If the ice is impermeable, you can't flood the surface. So, and we believe that this process, as the ice thins and you get more precipitation as a consequences of global warming in the Arctic, will become even more important in the Arctic as well. The permeability of the ice also constrains the evolution of salinity profiles. This is just sort of a schematic diagram, actually data going back to 1927, showing some of the dramatic changes that you see in salinity profiles. Currently, in global climate models, these salinity profiles are assumed to be constant. But the salinity controls the brine volume fraction, which controls the permeability, and it's all intertwined in itself. And so this is just a way oversimplification of what's actually happening in the ice. As you move the brine around, you get enhanced thermal transport and better exchange of heat between the ocean and the atmosphere. And of course, as you flood the surface, you can dramatically change the microwave signature that you see in remote sensing. As I mentioned before, the ice albedo, the ice pack albedo, is controlled by the melt pond, by the evolution of these beautiful melt ponds on the surface of the Arctic sea ice. The melt pond evolution, in turn, is controlled by the permeability of the ice, which is in turn controlled by the brine microstructure. When I look at these, I see again a two-phase composite material with all sorts of connectedness issues and all sorts of interesting structures that are happening and evolving on the surface. Now, as I mentioned, the flow of fluid is very important for the sea ice ecosystem. Here's a typical part of the complex ecosystem in the Antarctic where those killer whales are spy hopping to try to eat the penguins, and the penguins try to eat the krill. But the krill and pretty much everything is based on the sea ice algae that live in the brine inclusions in the sea ice. These are sort of the base of the whole food chain, both in the Arctic and the Antarctic. And their nutrients, so this is actually showing some of these brown algae, or they're green, yellow, there's all different sort of shades. But their nutrient replenishment processes are controlled again by this ice permeability issue. And we've seen this in the past, but also just in the most recent sort of American expedition that was companion to our Australian expedition during the International Polar Year. They could see very clearly how biological activity turns on and off according to my rule of fives, basically. You see the biology ramping up, and then it shuts down, and then it ramps up, then it shuts down, and it's all according to the subtle permeability of the ice according to my rule of fives. Another interesting issue here is one of the ways that algae live and the bacteria lives in the sea ice is through extracellular polysaccharide substances, exopolymers, algal mucus for short. It protects them against osmotic shock. It's basically a cryoprotectant like antifreeze, depresses the freezing point, and also provides a physical barrier from the ice crystals. And actually, we have some work. And it also gums up the ice, and it changes the permeability, and actually changes the distributions of brine inclusions. We have some work going on with Jody Deming at University of of Washington, who's actually a famous astrobiologist. And so astrobiologists are very interested in sea ice as well. Namely, there have been speculation as to whether sea ice, algae, and bacteria are proxies for possible life forms in extraterrestrial bodies, such as Europa, where it's believed to be covered with, say, a 10-kilometer thick, basically Epsom salts type ice. And so, but you know, there could be a lot of the kinds of things that I'm talking about, including even universal critical exponents, we think should apply to Europa, actually. And so I'm actually just itching to go there and sample the ice there. And so if anybody wants to come. So how do you describe slow viscous flow in a porous medium? Well, Darcy's law, where the averaged fluid velocity is related to the pressure gradient by I guess I would call a fluid conductivity, which is the denominator is the viscosity, but the numerator is this fluid permeability tensor, and that basically depends only on the geometric characteristics of the pores. This is an example of the field in mathematics that one of the fields in mathematics I sort of work in, called homogenization, which is the mathematics for analyzing effective behavior of heterogeneous systems. We start with Stokes equations for fluid flow through a porous medium. Here with a length scale of epsilon, one does what's called a two-scale expansion, and then the macroscopic or averaged equations become then Darcy's law, and that's how one derives this effective fluid permeability tensor, and ultimately this divergence-free condition for the average fluid velocity. And before our work, there was essentially very few measurements of the permeability of sea ice, and there was no theory whatsoever. So over the past several years, we developed a unified approach to understanding permeability in sea ice, first based in homogenization, Darcy's law, rigorous bounds, percolation theory, hierarchical models, and network models, and I'll touch on these various mathematical advances in this field, all validated with laboratory and Arctic field data. But also, one of the main contributions that we made was looking at the brine inclusions. People would take slices and then photograph them and try to sort of reconstruct. But we started doing X-ray CT imaging and then applied pore structure analysis to provide a really unprecedented look at the thermal evolution of the brine phase of these brine inclusions and how their connectivity evolves. This is a cover of Geophysical Research Letters, sort of showing homogenization played out. Namely, how this is some of our brine tomography, showing some of the brine inclusions, and how these small-scale these small-scale features and structures affect much larger-scale phenomena, such as the evolution of Arctic melt ponds shown here, and how we use mathematics to do that. So first, a few words about bounds on the permeability. I've spent a lot of time in my career getting bounds on effective electromagnetic properties of composites. The simplest example is so-called arithmetic and harmonic mean bounds for the electrical conductivity of a two-phase composite of conductivity sigma 1 and sigma 2 in the volume fractions P1 and P2. These are optimal bounds in the sense that if the electric field is in the vertical direction, this one achieves the upper arithmetic bound. That one perpendicular achieves the lower harmonic mean bound. This was first found by Wiener about 100 years ago, and we wanted to do an analog for fluid transport like this. And it turns out that there wasn't much similar bounds, actually. It was really interesting to us, but it turns out that vertical pipes with appropriate radii maximize the vertical permeability, but there's now a length scale in the fluid problem that you don't see in the electrical problem that makes it much more challenging from a mathematical perspective. We actually started working with these vertical pipe bounds, and then I decided to ask my friend and colleague Sal Torquato at Princeton, who actually had developed a much more general case of so-called optimal void bounds, of which our pipe bounds were sort of a special case. But again, this is like 100 years later. The sort of the analogs for the fluid problem were not found, and were finally found. And instead of analyzing the permeability directly, we analyze it using a trapping constant for diffusion processes in the pore space. You start with a diffusing tracer with concentration C of xt, which reacts with traps on the pore boundaries, described by this heat or diffusion equation. D is the diffusion constant, G is the reactant source rate, kappa is the surface reaction rate. With this boundary condition where the diffusing tracer is allowed to interact with the boundary. and then you look at a scaled concentration field, and that defines the trapping constant and the so-called diffusion controlled limit. One can derive a variational inequality for that trapping constant, which is inversely proportional to a mean survival time, roughly speaking, what's the average time that a diffusion process in that pore space can go before it hits the boundary. One can use variational analysis, and where one puts trial fields into these energetic definitions and gets a general bound like this involving the porosity phi and a length scale defined by these correlation functions in the pore space. And then one evaluates these general void bounds for so-called Hashine-Strickman coated sphere and coated cylinder geometries. These are very important, played an important role in the theory of bounds for composite materials. They have these beautiful fractal type structures. One then can get a general lower bound for the trapping constant this way, and then there's a general upper bound which bounds the inverse of the trapping constant to the permeability, and we work out these bounds for the so-called log normal distributions that have been observed for the brine inclusions in sea ice. And actually, it turns out my colleague Jing Zhu was able to do that very quickly because he worked on Wall Street for a couple of years. He was really used to working with these log normal distributions, which tend to describe certain aspects of stock prices. And so I thought we'd be orders of magnitude, with such a simple geometry, I thought we'd be orders of magnitude off. But nevertheless, we very nicely capture all of our laboratory and Arctic field data. There's the bound showing that it captures all of our data. Interestingly, this problem of diffusive trapping and survival takes us back to so-called nutrient uptake by bacteria in a fluid-filled porous medium. Same kinds of equations come up, and also NMR imaging of a porous medium. Now on to some theoretical predictions using percolation models. So the lattice percolation model got a lot of its, and particularly the random resistor network, got a lot of its early work in the physics of semiconductors. And this is an area that I've worked in a lot in these so-called percolation models, where you start with, say, a 2D or 3D lattice. With probability p, a bond is open, say with conductivity sigma naught. With probability 1 minus p, it's closed. P equal 1/3. Here's sort of impermeable ice. The fluid tries to get through, but there's no connected pathway. Here's permeable ice at 2/3. It might be a tortuous pathway, but it gets through. The effective conductivity, there's no conductivity below this threshold, which is 1/2. So it's these path lengths, sort of on average, or these open clusters grow, and there's a critical point, the percolation threshold, where they finally diverge, and you get pathways through the medium. And one can rigorously show that that's 1/2 for a 2D square lattice. But we need 5% for sea ice. This was sort of the moment I saw these. I was out in the middle of a storm in the Antarctic about midnight with winds blowing 60 miles an hour, and I saw brine percolating up to the surface. And I knew about the microstructure of sea. I said, that's got to be percolation. And so that got me thinking about all this. And but the first issue was, 50% for a 2D model. It's about 30% for a 3D model. How do you get 5% brine percolation threshold in sea ice? So it turned out that they had a similar kind of situation when engineers were designing so-called stealthy or radar-absorbing materials. They needed about 30% volume fraction of carbon black or silver particles to get the kind of conductivity and radar-absorbing characteristics that they wanted. And so they realized, though, if they use so-called compressed powder microstructures, big polymer particles and small metal particles, and then squash it down, you could achieve the appropriate electromagnetic properties with arbitrarily small volume fractions. And so I just simply realized, sea ice looks a lot like that, and I applied their compressed powder model, and out popped 5%, which explained all sorts of Antarctic data on ice production and algal growth.
So is the 5% sort of like the percent at which percolation occurs?
In a sea ice microstructure, yes.
And
Yes.
that depends on the kind of geometry.
Exactly. So we've just realized that in frazzle ice in the Antarctic, there's maybe a 10% threshold that's more relevant actually there. But And so, but at the time, as a mathematician, we had no direct evidence. We had no direct way of looking at the brine conductivity. Now we do with this X-ray tomography. So here's no vertical pathways, one vertical pathway, many vertical pathways. We map 3D images of pores and throats onto 3D graphs of nodes and edges, and then we analyze that graph conductivity as a function of temperature and sample size. By the way, these images are very similar to the bone microstructure. We've also there are these key functions in percolation theory that people have plotted and calculated for years in lattice models, but nobody's done it for a real material. You can't, for example, you can't turn a knob and change the porosity of a rock, but you can turn a knob and change the temperature of sea ice. And so here's the divergence of the vertical correlation length in sea ice. We've also been able to use finite size scaling techniques in physics to estimate these percolation thresholds. This is a little tour through the brine microstructure of the sea ice. Terms of transport, there are these critical exponents that describe the takeoff of the permeability and the conductivity. They're believed to be universal for lattices. There was a small industry in physics trying to estimate these things. The numerical estimates range from 1.5 to 2.4 for the critical exponent in 3 dimensions. I proved a rigorous inequality that it had to be less than or equal to 2. Of course, in the continuum, you can get so-called non-universal behavior, such as the Swiss cheese model. However, these non-universal exponents arise from a singular distribution of local conductances. But in sea ice, this distribution is log normal. And the permeability exponent for sea ice should then be 2, this universal exponent. We've also used so-called critical path analysis, originally developed and doped for hopping conduction and doped semiconductors to estimate the scaling factor in front that, roughly speaking, bottlenecks control the flow, basically, in a situation with large range of conductances. And then we get this deceptively simple formula for the permeability of the ice. There's the universal critical exponent. There's the scaling parameter. Sedimentary rocks like sandstones live in the same universality class. Here's sort of the raw data taking off above 5%. And then there's our theoretical prediction, 2x minus 7.5. The 2 is the universal law. And there's our statistical best fit of the data. We get quite close correspondence with the data. We use self-similar hierarchical models for porous rocks to get a much broader range of brine volume fractions, not just near the percolation threshold. There's our theoretical predictions, and there's actually percolation theory is like a higher order correction. We get, again, excellent correspondence with the data. We've also developed some network models. I saw a network model poster out there. We use that to model the flow of fluid through sea ice. We've also been modeling thermal conduction, now that we know how the brine moves around, to try to use the advection diffusion equation to model the flow of heat through there. And we see that we can get a very enhanced thermal conduction coefficients as above the percolation threshold. And then finally, before I show you the video in a minute, we've also been looking a lot at remote sensing of sea ice, which is fundamentally an inverse problem. There's all kinds of parameters we'd like to measure, especially the thickness, the extent, say the roughness, transport properties. The key parameters, the complex permittivity of the ice, which I've been very interested in for a long time. Here's the quasi-static Maxwell's equations when the wavelength is long compared with the microscale, which then defines the effective complex permittivity in this way, very similar to Darcy's law, actually. And there's a very beautiful method that I worked on a long time ago in my PhD thesis, at least the beginning of my PhD thesis, where one looks at this function. H is the ratio of the component parameters, and it's a beautiful analytic function. It takes the upper half plane to the upper half plane. It's analytic off the negative real axis. And then an auxiliary function, one can get a very beautiful and powerful integral representation based on the spectral measure of a self-adjoint operator, which incorporates all the geometrical information about the composite. And say the mass of that measure is the porosity of the composite material you're looking at, such as sea ice. You get all these bounds in the complex plane. This is just the sort of the simpler ones where you have assumed only the volume fractions, and then you further assume isotropy. This is some comparisons with some data that was taken in the Arctic. This kink in the data, that's about 5%. This was the first evidence we started to see a percolation transition in the electrical properties. And we've actually followed that up much more. We have a lot more plans in that direction. We also invert that electromagnetic data for the porosity of the ice. and then one of my colleagues has been using those same ideas so that bone porosity can be estimated from the effective torsional modulus using reconstruction of this so-called spectral measure to help out in monitoring osteoporosis. The bottom line is, and that's why you should study math, the math doesn't care if it's bone or ice or whatever. That's the power of mathematics. And then finally, this was our most recent expedition down to the Antarctic. We actually made the first measurements of permeability in the Antarctic ice pack. We did surface impedance tomography, where we had probes on the surface to invert for the conductivity profile. But then, to relate the electrical properties to the fluid permeability properties, we did the first measurements where one actually extracts cores and then puts our Wenner array there to make directly measure the vertical component. We also did tracer studies where we poured fluids through the ice. This is impermeable ice and slightly permeable ice. This is me measuring the permeability. All my friends down there have multi-million-dollar instruments, so I like to call this my million-dollar meter stick. This is showing some of the difference in microstructure. We discovered that the granular ice that's so prevalent in the Antarctic has a different threshold, a rule of tens, as it were. Also controls the exchange CO2 fluxes moving up and down through the ice. This is sort of a really new area of research. People are just starting to look at this now. And again, the permeability of the ice controls it. These are our electrical measurements. This is our setup to measure the vertical conductivity. Again, percolation theory describes these processes now beautifully. Some of my colleagues found exactly the same kinds of data in the Arctic as well. This is really surprising to me. It fits together beautifully and is all described very beautifully by this universal exponent in percolation theory. This is our tracer experiments. We're now monitoring all this, trying to reconstruct these spectral measures using cross-borehole tomography. This is some of the work going on in the Arctic and some of the reconstructions of the resistance profiles in the sea ice. And then finally, why are we doing all this? Well, we'd like to represent some of these key processes better in sea ice. This is one of the most widely used models that says by the middle 21st century, the Arctic ice pack will be gone in the summertime. And so I've shown you that brine flow through sea ice is a key to the geophysics and biology of the polar regions. We've developed a comprehensive theory of fluid permeability using mathematical techniques mostly from solid-state physics and semiconductor physics. We've measured sea ice transport properties in the Antarctic, and now these key processes can be modeled much more realistically and put into climate models. Thanks to NSF and the Australian government for funding this research. You can read much more about this in the notices of the AMS. This is like the May issue of 2009. And you can go to this website, mathaware.org. I was the national chair for Math Awareness Month, where the topic was mathematics and climate. We had world-famous climate scientists writing about and interviews on how we can use mathematics to better understand these climate models. So what I'd like to show you now is a video that I made in the Antarctic. I took 4 widescreen high-definition cameras down there to get some good images. And if the lights could be, thank you very much. Okay. This will just take a second to. Okay. So you'll first just see some opening scenes of the aurora moving through the ice, through grease ice. And this is SIPEX, the Sea Ice Physics and Ecosystem Experiment. And we did this in the international polar years off the Southern Ocean, off Wilkes Land, Antarctica. And this was this was Australia's main contribution to the International Polar Year, worldwide activities in trying to look at the polar regions. Okay, so here we are leaving the home port of the Aurora, Hobart, Tasmania, the home of the Tasmanian devil. This is now crossing the Southern Ocean, and I just love this. Fortunately, I don't get seasick. My student Adam did get seasick, so he was up in his bunk for about a week. About 300 feet long. This is pretty typical. So now I'm looking through the porthole in the dining hall, and now, so this is pancake ice in the marginal ice zone, and you get these ocean swells that propagate. It's a beautiful Fourier analysis question. Just these beautiful, purely sinusoidal waves propagating. I've seen some huge ones in really big ice. It's one of the most hypnotic phenomena I've ever seen. This is the pancakes coalescing to form the ice pack. And now I'm sitting in a hole in the hull that it gives you the feeling of being right on top of the ice. Here are some penguins escorting us along, porpoising along. And here's the aurora breaking through some very, very thin ice. This was September, October, so like the Antarctic spring. This is our ice stations where we go out onto the ice. These are the trace metals people. This is doing snow and ice thickness transects.
Freeboard 68.4.
This is doing some of the radar work for measuring the thickness of snow. You see it's a little difficult to operate in this environment sometimes. It gets real cold, as you can imagine. And here's a helicopter. These were very important, not only for the scientific experiments, but for helping us get out when we're stuck. This is one of the the Warbot EM induction device for measuring ice thickness. This is out in a storm, and my student Adam is shoveling the snow, not just because I made him do it because he's a grad student, but because we really needed it uncovered.
My name is Kazu Tateyama. I'm from Japan. I'm using this instrument for measuring sea ice thickness.
Here I am setting up our surface impedance tomography experiments, our Wenner array. There's our 1960s era box that we used.
This is 13
literally.
ohms.
Here's some of the locals. And these are the emperors. They're very bold. They come right up to you. And then his friend's going to come by. And you really have to wonder, like, what do they make of all this? What are they thinking? No, they're not penguins. Yes, I think they are. This is a snow pit measuring the properties of the snow, particularly for remote sensing purposes, looking at its density. These are the trace metals people. Even they were using our rule of fives. It's sort of like to know where to drill to get the brine. These are the oceanographers. They use these big holes, and leopard seals will come up out of those holes, grab you, and try to drag you down and eat you. I kid you not.
Profile measures the water velocity in the column 60 to maybe 120 meters beneath the ice.
And here's a penguin eating snow. And this is like a famous penguin being harassed by the paparazzi. He doesn't seem too phased, though. She's looking for EPS. She's looking for the EPS signal from the bacteria and the algae. This is me starting our permeability experiments. Here's impermeable ice, slightly permeable ice, and then we use the rule of fives to try to know where to drill, knowing the thermal profile, to try to figure out where that critical threshold was. And it was very difficult because there's not too much ice in the bottom. You got to get pretty deep. And then now we got it. And you see the brine coming up, and we measure that rate. We measure the rate at which it comes up the meter stick to measure the permeability.
40 seconds.
Now the Antarctic Chainsaw Massacre. This was our blocks of ice to try to pour fluids and tracers. I started pouring beet juice about 10 years ago through the ice, and now I have these professional tracers that I use to get a feel for the fluid flowing through the ice.
I'm a field ecologist, and I'm working here on a bio-optics site, and we take an ice core to look for chlorophyll and compare these data with under ice irradiance data, which we measure with this radiometer, which is lying over there in the snow.
And now we're going to go underneath the ice with a remotely operated vehicle. And now note that the ice is nice and smooth on the surface, but underneath, a lot of rafting. This is this ridging and how the ice, it's like 50 centimeters is like a typical thermodynamic block, but then they start piling up on each other and you get much thicker ice. So as I said, the helicopters were very important. Not only they did thousands of kilometers of sorties away from the ship. Here's some of these the beautiful icebergs, and then there's a nice look at the ship. Now talk about being in the middle of nowhere. These poor little guys. A long way to go. This was like an ice jet. None of us had ever seen this before. This is all sea ice. On the bottom it's moving, on the top it's not. You can see the mismatch there. And this we call dragon skim. Again, like pancakes flipped up on their sides. None of us had ever seen this. Like 50 centimeter relief on the surface there. This is vortices being shed by the crane in a storm with a light beam going through it. And now when one of these 300-foot-long orange ships moves through the ice, it seems that all the little critters there tend to scurry away so they don't get run over. And these are the little Adeles. They're usually a little more afraid than the emperors. And this is some of the algae ice, just turned up on its side, broken up by the ship, and some more algae ice popping up. And this is the trawl deck, doing fishing for krill and fish and other things. Now we're leaving the ice pack. You see the swell coming back. There's the warbot still measuring thickness. This is the crane we used to have to go out onto before they got the brow. Doing just a last few measurements. And that's a leopard seal. Those things are massive. They're about like 15 feet long with a massive head and big teeth. And for some reason, he's just out there all by himself in the marginal ice zone in those big waves. And this was our last look at the ice edge. Our last look. And then I got very excited because we hit basically a hurricane-force storm 2 days out of Hobart. Now we're 70 feet up here. And look at that wave going by. This is what I've been waiting for. And so now you get some nice, beautiful waves in the Southern Ocean. This is where they have that Hobart to Sydney yacht race, where there was a major disaster several years ago. A lot of people died, and you can see why. Pretty treacherous. Now this is, again, this is a massive ship, and look at how it's just getting tossed around. I tried. Now you finally, that's me, where I'm definitely not supposed to be, right down on the ocean level. And if I got sucked out, that would have been it. So that's what I was looking at, was these waves way up over my head. And then I finally got nailed, and I got completely soaked. And I had to go back to my room and get everything dried out and stuff. So anyway, thanks very much for your attention.
Because you do have milk cards, so just to make sure there's enough for everybody. But if you do go through the regular line, please join us at the table. There'll be room for everybody. Okay, so let's take a couple questions.
Yeah.
Well, last night, one of Rachel's questions posed was what sort of things students might be lured into. And this
Yes.
catalog of yours was really interesting. But now, you're from the University of Utah, and I don't think there's any glaciers
There's
around
none.
there. So what is it that led you into this bipolar behavior?
Skiing. That was what lured me to Utah along in 1991. I was at Princeton and NYU before, at Rutgers before that, and it was skiing that's why I went to Dartmouth, where they had their own ski area. I was a ski instructor there, and but I didn't anticipate. I went there because it's skiing, excellent math department, it was very good applied math. But over the years, I was able to build up a large group in mathematics of composite materials. And that's sort of where, that's where I'm really coming from. I have no training whatsoever in geology, geophysics, climate, sea ice, any of these things. I mean, I started out very young studying sea ice, but I never had any training in any of these. So it was more, as a place to go as a mathematician, but also skiing. So, yeah. And somehow it's evolved into, and then as the ice started melting, it's like, well, now it's gotten very active. So, yeah.
Does the ship get stuck in the winter ice?
Absolutely. Yeah. One time we had to come back 2 weeks early because we were backing and ramming so much over a 3-day period. It wasn't that the ice was so thick. It was that there was these incredibly strong winds that were causing all the stress, and so we just couldn't get through. And so it was anyway. So we wasted all our fuel. That we had to go back. Captain had to pull the plug. We had to go back early.
Do you have to winter up there at any point?
I'm sorry.
Did you have to spend the winter up there?
I've always been, except for once, I've been down during the winter, but I've never actually spent the entire winter. So.
Was it winter down there?
Yeah. Oh yeah.
Oh.
It's winter down there. Yeah.
Not good for you.
So one physics question. As you probably know, in polycrystalline metals, they also have a log normal grain size distribution
Oh.
that governs the grain growth dynamics. Why are the brine inclusions log normally distributed? Do you know?
I don't know. I don't know, and I'm not sure there's really ever been. That was the there was a fundamental piece of work from Don Perovich and Tony Gow, who I used to know as when I was an undergraduate working there, and that's what they found to be the best. That fit the best, and however, I don't know if there's been any fundamental work done on why that's the case.
Nobody's ever come up with a convincing explanation.
Yeah. Okay. Well, so I guess it's the same. It's the same here. Although there are some microscopic studies going on from sort of a fundamental kinetic theory and also Ginsburg-Landau theory. There's more, microscopic at a much lower level work that is going on to try to understand the development of brine channels and brine inclusions and so on. So who knows? Maybe that would be the natural place for at least a good physics explanation to come from, I think. So, yes.
Maybe you discussed, I'm not so sure. So this DLA model of the brine formation,
Yes.
does that play a role in your study of the permeability of this?
It does not at this point. That's a really good question. I'm actually interested in that kind of stuff for much deeper mathematical and physical reasons related to these ER fluids. However, it is amusing to me also that although DLA sort of comes up naturally when you look at fluid flowing through a porous medium and actually interacting and melting and so on. So, and I haven't looked too much at that myself at this point. Although that's one of those things that I want to look at much more deeply because I think there's some interesting mathematics and I think there's some interesting things going on there.
It seems you have already a good idea of how to study the permeability of the sea ice without knowing this finer structure of it.
Correct, and that's in some sense, like this universal critical exponent. That was one of the things that I found most fascinating was that this universal exponent, which only depends on dimension, and is the lattice exponent. That actually describes sea ice. Now we found, not only does it describe the permeability of the ice, even when you look at this granular ice, where there's a different percolation threshold, but that's what you see in lattice models. It's like you change the details of the lattice from triangular to square to hexagonal. You change all the gory details of the lattice, but the critical exponent stays the same. It depends only on dimension. And that's what we're seeing in sea ice now. In other words, you can change the percolation threshold, the details of the so-called geometrical structure at the small scale, but that critical exponent captures the deep statistical physics that are happening in some sense. But now we're seeing that it describes the electrical conductivity as well in our new experiments that we did in Antarctica the last time. So so I'm not so sure that that's going to help you in understand. I think it will be important for the biology, I think, because that's where these guys live, and the kind of local small-scale structure that you see is very important for appropriate modeling of enzymatic diffusion processes and nutrient replenishment and these kinds of small-scale processes that are important in the biology. So I would suspect that.
But the main challenge is then to incorporate that into the climate.
The larger, yeah, exactly. Going up a couple scales. That's right. That's where a lot of the challenge and a lot of the interest is, because it's not been incorporated into these things. Yes.
Sort of a climate change question. I was wondering if people have any guess as to whether there were periods in previous interglacials when there was no.
Yeah, that's a really interesting question. That's a really interesting question, and I'm not so sure. There are people that focus on paleo sea ice studies. Basically, there's proxies in terms of the stuff that the algae that filters down, and then they core the ocean sediment to get some idea of where the ice edge was and so on. And I haven't looked into too much detail into those studies and whether or not there really has been a disappearance. I would suspect, at least on long enough timescales, of course. But continents move around. There's all sorts of stuff that happens on much larger time scales. So, and that's a really interesting question, and I'm asked that a lot actually. I should probably look more into it, and but I don't know off the top of my head.
Can you just make a comment about CO2 permeability? That could be awfully important.
Exactly. Yeah. This is all brand new stuff, and basically the general picture for a long time was that the equatorial oceanic regions are sources, the polar oceans are sinks for global CO2, and of course this is a big question. It is an important question, of course, for absorption of CO2 that's in the atmosphere and so on, and basically this point of view that there's this porous permeable layer that sort of has an on-off switch in some sense. It's all. I mean, I basically published a science article back, I guess 11, 12 years ago, and it's really in the last 4 or 5 years that it's really starting to, no pun intended, but permeate the literature and our view of what happens with sea ice. And only now, just because of more very recent experiments, are people starting to look at gas exchange processes such as CO2, and only just on these last couple of expeditions and some work I know going up on the Arctic, has it been started to observe that there actually been that first-year sea ice appears to be a source with a net outflux of CO2 in newly forming ice. But nobody knows what's going on. I mean, there could be biological connections. There could be subtle chemical contributions. So I have a close colleague, Jean-Louis Tisson in Belgium, who thinks knows a lot of chemistry and can sort of think about those kinds of processes and how that can affect things. But the bottom line is it's all being controlled by the structure by the permeability of the ice and the connected pathways, basically. I mean, no matter how you look at it, that's going to be controlling whether or not these exchanges happen, just as it controls fluid transport.
All right. Thank our speaker again.